This video is to go through the practice problems about types of collisions. Our first question is about a cannon and a cannonball. Question number 1 says, a 12-kilogram cannonball is shot from a 125-kilogram cannon. Assuming the cannon and the cannonball are both at rest before firing, calculate the recoil velocity of the cannon when the cannonball is fired at 105 meters per second. Now, these collisions problems can get a little bit confusing because you're dealing with so many numbers. There's only a few variables, but there's a whole lot of numbers to figure out where they go. So I like to start with drawing a diagram to represent my different objects. So I've just got a box here that's labeled P1, so the momentum of the first object, is equal to, and this box here labeled P2, momentum of the second object. So I know that one momentum is equal to the second momentum. Now I'm going to take what I know and plug it in to figure out what I'm looking for. So my first object I'm going to say is the cannonball, just because that's the first one that's listed in the question. It doesn't matter which one you call number 1 or number 2, as long as you keep all of the information straight with that object. So my cannonball has a mass of 12 kilograms and a velocity of 105 meters per second. And we know that that's going to be equal to the momentum of the cannon itself, the cannon having a mass of 125 kilograms, and we don't know the velocity. So let's plug that into our equation. We know that momentum is mass times velocity. So 12 times 105 is 1,260 kilogram meters per second is equal to 125 kilograms times some velocity. We want to get the V2 by itself, so we're going to divide both sides of our equation by 125. So 1,260 divided by 125 gives us our recoil velocity for the cannon of 10.1 meters per second. Basically what that's saying is when you shoot this cannonball out of this cannon, if the cannonball moves forward at 105 meters per second, the cannon is going to be pushed backwards or recoil backwards at 10.1 meters per second. Question number 2, the plastic ball collision. Now this is an elastic collision problem. And we know that because we have two separate objects before the collision, and we still have two separate objects after the collision. So we have, again, our boxes to represent the objects, just labeled P1 plus P2, so that's before the collision, is equal to P1 prime, prime meaning afterward in this case, plus P2 prime. So the momentum of 1 plus the momentum of 2 is equal to the momentum of 1 after the collision plus the momentum of 2 after the collision. Now let's look at what our question says. A 2.1 kilogram plastic ball has a forward velocity of 0.31 meters per second. It collides with a second plastic ball of mass 1.1 kilograms, which is moving in the opposite direction at a speed of negative 0.44 meters per second. After the collision, both balls roll away. The 1.1 kilogram ball is now rolling at 0.26 meters per second. What is the new velocity of the first ball? So let's block out what we know. I know that before my collision, the left side of my equation, I have a 2.1 kilogram ball that's moving at 0.31 meters per second. I have a 1.1 kilogram ball that's moving at negative 0.44 meters per second. Now, why is it negative? It's negative because it's moving in the opposite direction from the other one. We know that this first ball is listed as going forward. If the other ball is going the opposite direction, we have to indicate that somehow, and that's what the negative is for. That just tells you they're going the opposite way from each other. Now, after the collision, I don't know how fast my 2.1 kilogram ball is moving. That's what I'm looking for. I know that my 1.1 kilogram ball is now moving at 0.26 meters per second. So that should tell you that this 1.1 kilogram ball has switched directions now. It's bounced off of the first one and it's going the other way. But I want to know how fast the first ball is going. So let's plug all of these numbers in to our equation and see what we can do with it. So when you get the momentum of the first object, 2.1 times 0.31, that gives us a momentum 0.651 kilogram meters per second. Plus the momentum of the second ball, 1.1 times 0.44, negative 0.44, gives us a momentum of negative 0.484 kilogram meters per second, is equal to 2.1 kilograms times some velocity, plus the new momentum of the second ball, 0.286 kilogram meters per second. This looks really long and complicated, but we're going to go through it step by step. Make sure that you're writing down all of this work too, so that you have something you can refer back to if you have questions. So let's rewrite what we already did. Momentum of the first ball plus the momentum of the second ball before the collision is equal to the momentum of the first ball plus the momentum of the second ball after the collision. Now all we have to do is combine like terms. So 0.651 plus negative 0.484 gives us 0.167 kilogram meters per second. Notice I haven't changed the other side yet. I'm not even doing anything over here yet. I'm just combining my terms here. Now I have another momentum, another kilogram meters per second. I want to move that over to the other side of my equal sign. So if it's added on this side, I'm going to subtract it over here. So 0.167 minus 0.286 kilogram meters per second is equal to our 2.1 kilograms times some velocity. When I add those together, I get negative 0.119 kilogram meters per second equals 2.1 kilograms times some velocity. Now I want the v by itself, so I'm going to divide both sides of my equation by 2.1 kilograms. So negative 0.119 divided by 2.1 gives me a velocity of negative 0.057 meters per second. So what this is telling you is that the first ball after the collision is moving at this velocity. The negative tells you that it has switched directions. And the third question, this is going to be an inelastic collision where our two objects stick together. So again, I draw my little boxes to represent what's happening. The momentum of the first object, separate, plus the momentum of the second object, separate, before the collision, is equal to the combined momentum of the two objects afterward. So let's see what our question says. Jenny, who has a mass of 41 kilograms, is ice skating and traveling at 4.1 meters per second north toward Anthony. Anthony has a mass of 65 kilograms and is traveling at negative 12 meters per second south toward Jenny. As the two approach each other, Jenny suddenly grabs Anthony's hand. The two then continue skating together holding hands. What is the final velocity, including direction, of Jenny and Anthony skating together? So I'm going to block out what I know. My first object is Jenny. Jenny has a mass of 41 kilograms and a velocity of 4.1 meters per second. So her momentum is going to be those two multiplied together. My second object is Anthony, 65 kilograms and negative 12 meters per second. Again, the negative indicates that he's going the opposite direction. That was indicated in the question as well when it said that Jenny was going north, Anthony is going south. Afterward, I'm going to add those two masses together because they're moving as a single object. And what I'm looking for is how fast are they going. So let's multiply those out and see what we have. So 168.1 kilogram meters per second is Jenny's momentum, plus negative 780 kilogram meters per second, Anthony's momentum, is equal to 106 kilograms, that's their total mass, times some velocity. I'm going to combine these together and get negative 611.9 kilogram meters per second equals 106 kilograms times some velocity. I want to get V by itself, so I'm going to divide both sides by 106. And when I plug that in my calculator, I get their combined velocity of negative 5.8 meters per second. Most of the time you can leave it like this. That negative does indicate direction, but just in this instance, so I know that you understand, I want you to tell me, is that north or south? Hopefully you recognize that because Anthony had a negative on his velocity and he was going south, this negative also indicates that they're going south together.